The next speaker is going to be Zubin. I think everyone knows him and he doesn't need an introduction. And he's going to be talking about the Automatic Statistician and some updates on this project.
Okay, so I've got a short talk slot, and I'm going to try to summarize maybe things that we've done since we presented the Automatic Statistician here, actually in this meeting 3 years ago. So that's what the project update is. But because everybody doesn't know about it, I'm going to give some background. We're going to use probabilistic modeling as a framework for doing machine learning. I'm just going to go through this stuff quickly. We love this equation, Bayes' rule. It tells you how to update your beliefs about hypotheses given data. And in a Bayesian's world, there are only two kinds of things that you measure and observe. That's what we call data. And everything else, that's what we call hypotheses. So this is a sort of general way of updating beliefs given data. And I have to show my obligatory Bayesian machine learning in one slide. Everything follows from the sum and product rule, and it's a nice framework for learning about parameters given data, for making predictions as a form of averaging over different hypotheses, where the averages are weighted by the posterior, and also for doing model comparison. And we're going to end up using some of these concepts in the Automatic Statistician, if you haven't seen that. So just as a couple of things I wanted to say, in machine learning these days, deep learning has been spectacularly successful. And it's easy to sort of lose sight of the fact that not everything can be solved just by throwing a big, deep neural network at it. And one of the things that I think is important is, well, these are not really contradictory things. Deep learning architectures are very powerful tools for learning functions of different kinds, differentiable tools for learning functions. But kind of at a slightly higher level, is it still useful to think about probabilities within machine learning? That's a good question we should ask ourselves. And at least in my view, there are certainly certain situations where probabilistic modeling is essential. And that is basically wherever we need to capture our uncertainty well. So for problems like forecasting, decision making, learning from limited, noisy, and missing data, learning complicated personalized models where you might have a small amount of data from each individual person or client or subject. Data compression is all about probabilistic modeling, and I think most relevantly to this talk, if we want to automate sort of scientific discovery or getting machines to sort of discover plausible explanations from data, this is a place where probabilistic modeling is actually a very nice way of thinking about that problem. So as some of you might know, I'm now working also at Uber. And so why would Uber care about something like probabilistic modeling? And I've just reproduced everything that I had on the previous slide here with just a few examples. So I mean, essentially what's happening at Uber is that we're really looking at machine learning in the real physical world. We're trying to understand cities. We're trying to understand drivers and riders. We're trying to predict supply and demand. We're trying to build self-driving cars that are knowledgeable of their uncertainty. This seems like a very important thing, so that they can make sensible decisions and maybe hand over control when they're in a situation that they haven't encountered before. And for all of these sort of prediction problems, modeling problems, business intelligence problems, even mapping problems, self-driving car problems, actually, when you look at them, uncertainty plays a hugely important role. So anyway, that's the one slide about that. The theme of the talk today is automating things. And automating things is basically what I'm obsessed with these days. I'm kind of, this is the one slide description of things I'm interested in. And basically, it all comes from the fact that machine learning is bizarrely, for a field that is supposed to be about learning algorithms, it's still very human intensive, right? There there's some very highly paid expert there tweaking something to get it to perform well on some data set. And that doesn't really need to be the case. We'd like to be able to automate or semi-automate all different aspects of machine learning. And I'm going to talk mostly about the automatic statistician, but I'll briefly mention other topics which I know are of great interest to Microsoft Research Cambridge as well, like probabilistic programming and computational resource allocation and so on. Okay, so that was background. We're going to automate machine learning. Isabel already talked about some of our collaborative work on automating the discovery of the statistical types of latent variable, of observed variables from data. The interesting thing about that work is when we were doing it, we were trying to come up with references to previous work, and actually nobody's done this as far as we can tell. If you know of anybody who's trying to do that, please let us know, because we didn't find anybody else doing that, although it seems like a hugely useful, important thing to do. But there are a whole bunch of other things in the pipeline, like automating feature transformations and understanding data collection and experiment design. We should be aiming to do all of this. And the automatic statistician is mostly focused on this bit here, which is automating model discovery and explanation. Okay, so just a bit of review, and then I'll do the what's happened since 3 years ago. So the motivation is there are not enough data scientists. We want to basically be able to do some of the data science tasks much more efficiently by having computers search over good models and find good explanations. And so that's where the genesis of this project came from. And the sort of pipeline of work is you give it some data, you upload some data, and then the system goes and searches over some language of models, evaluating models using some criterion that trades off the complexity of the model with the amount of data that you have. It finds a good model, and then it can use that model for the usual thing we do in machine learning, which is predicting on test data or validation data. It can also do something that is a bit more unusual, which is translate that model into a report. And it can, in various versions of the automatic statistician over the years, we've also tried to systematize model checking or model criticism, which is basically every time you do modeling, you need to ask yourself after the fact, well, does the model actually capture things that were in the data or not? Or can I find statistical properties of my data that are not well captured by my model? This is the classical model checking or model criticism. And this is not, sadly, this is not done systematically by humans, but we want our computers to be better than humans, so we're trying to do that systematically in the automatic statistician. So I'll switch now, because it's boring presenting old slides. I'll switch now to maybe a live demo. So here's the very classical, very small iris data set from 1935, used by Fisher in 1936 for the first classification paper. So here is a report writing demo. I keep promising we're going to put this back online. So you upload some data, and then it says your report is being prepared. And we used to produce PDFs that were formatted like NIPS papers, but now we've decided that maybe it's better to put it on a web page. And it's thinking. And then it starts producing a report. Okay. So there it is. Produces a report. This is a very basic version of the automatic statistician. We have more fancy versions, so we're just trying to merge all of the different versions together. We're nearly there because so many people have worked on little bits and pieces of this project and I haven't really managed this very well, that we're now, in the last 6 months, been cleaning up our act and merging all the software together into one single very nice code base with the help of a research software engineer who I'm very grateful to, Emma Smith. Okay, so here's a very simple version of this report. This is sort of taking this data, applying a bunch of different models to it, and then deciding that for this iris data set, a mixture of Gaussians model is actually the best explanation it can come up with. And then it does some visualizations of that mixture of Gaussians model. It also decides that there should be 3 Gaussians, which, if you know the iris data set, is kind of nice because there are actually 3 classes in this data. It gives you some visualizations and so on. We try to come up with automatic projections of the data that are good evidence for the 3 classes, for example. Okay, so this is a very, very simple version of the automatic statistician currently, and I'll show you some other versions that are somewhere in the code base, and basically we need to create an interface where you can switch between them. So the classic one that some of you may have seen if you've heard me talk in the last 3 years is one that does modeling for regression problems, and in particular for time series regression problems. And so we use Gaussian processes, and I'll skip over this quickly. We use Gaussian processes to model unknown functions. And Gaussian processes are related to all sorts of other fun things, which I'll skip as well. The nice thing about Gaussian processes is that, like other kernel methods, they're defined in terms of a kernel, and kernels are something for which we can define a nice grammar of models. So the basic idea is we have a few base kernels, like the squared exponential, periodic, linear, constant, and white noise kernel, which correspond to distributions over various kinds of functions. So these are just 2 samples from each of these, from functions drawn from kernels with that form. And then kernels are closed under addition and multiplication, so we can generate more complicated functions that way, like all polynomials and trends with periodically superposed variation on there, approximately or locally periodic functions, etc. And then if we apply this to time series data, then we start from a very simple model evaluating marginal likelihoods down this tree until we come up with a model where evaluating any of the children in this search space gives you worse marginal likelihoods, and then we have a model that then we need to explain, and that's what ends up turning into a report. So the translation from the abstract sort of statistical model into a report is something that is done with basically kind of canned phrases that correspond to different properties of these kernels. Okay, so here is the report for, actually here is the executive summary of an 8 to 10 page report for this particular time series. And here's just the first page of these reports. This is like the original old thing that we did. And this thing generally, just by being systematic, searching over models, you generally find better models than leaving it to a human, I would say. I mean, a very patient human will probably do better, but a typical impatient human who only knows a few models will probably generally try just a few kernels or models that person knows, and it's just better to be systematic, I think. Okay. Then we did some work on model criticism as well, and if you look at the reports that we have, there is a section at the end that tries to automate model criticism. We didn't do it in the very simple report that I showed you because it's hard. Model criticism is generally hard. But I think we should all aim to do some model criticism as well. So here's something else new that we did since 4 years ago, 3 years ago. This is an automatic statistician for classification. Classification is something that is like the bread and butter of machine learning. And we did time series, which is sort of not the bread and butter of machine learning. So let's go do classification. Well, the good news is we can, we could use other models, but we couldn't use Gaussian processes for classification as well, as you probably all know. And so here are some, here's an example of a report that was produced. This was by a master's student working on this, a report that was produced for classification. And I'll just show you some snippets of the kinds of things that are in the typical reports here. So it's trying to classify some output given some inputs. And what it's looking for is explanations of which inputs are relevant and which interactions are there in the data. So here is like the full model description it comes up with for this, this PIMA diabetes data set. It says the model involves an additive combination of variable plasma glucose and a two-way interaction between variables pedigree, function, and age. I think, I don't know, that seems like a plausible sort of explanation that an expert statistician might give you for the response variable's dependence on the inputs. And then, it shows you both what the cross-validated error is, what the negative log marginal likelihood is. It does a summary of the importance of each of the input variables compared to a constant baseline. And so, if you wanted to pick a single variable to predict on, it would be plasma glucose here. And then it also, I think, interestingly, when you try to explain the dependence of a variable on another variable, we have to think, well, what's a good explanation? And I would say one of the aspects of a good explanation is if you say things like the response variable increases or decreases with the input variable. Okay? Not that it's linear. I mean, linear is a very strong thing. But monotonic relationships, I think, are fundamentally intuitive and useful things to know about. So we actually do this. We sort of automate the discovery of monotonic relationships. So it says, for example, that the response variable, there's some evidence that the class label has a positive monotonic, it should be positive monotonic relationship to the input variable plasma glucose, etc. Okay. So that's the automatic statistician for classification. And again, we'll roll this out pretty soon. So I think I'm probably running out of time, Miguel, right? Okay. Yeah. So this is just a plug for Isabel, but she already talked about this. So I think that's part of the bigger picture. I think it's an important thing that has to be done. When you're actually trying to discover a good model out of a very large space of models on a potentially large data set, then you suddenly encounter a computational problem. And Bayesian inference, we all know, is pretty expensive. So we need to be rational about how we use computational resources. So as a sort of spin-out, but a really interesting spin-out of the Automatic Statistician project, we ended up looking at the rational allocation of computational resources, which is, I've got lots of models and a big data set. How do I, which ones should I try? Should I try them on small subsets of the data? And if something is promising, should I allocate more computational resources to the model that's more promising and less to the ones that are less promising? Well, we're going to automate all of that. We automated all that within the framework of Bayesian optimization, in particular this very nice paper by Stversky, Snook, and Adams called Free-Star Bayesian optimization. And we extended that a little bit just to handle the ability to build an ensemble model using this Free-Star Bayesian optimization. And again, I'll show you a live demo, and maybe I will stop there at the live demo of the Free-Star Bayesian optimization. Okay. Okay, so now this bit of the big automatic statistician project is actually not, it's doing Bayesian inference, Bayesian optimization to allocate computational resources to models which themselves are just good old-fashioned classifiers, okay, random forests and gradient-boosted decision trees and things like that. So we load up the data. And the server goes to sleep if I haven't hit it for 20 minutes. So I think it's just waking up. We load the data. It's not because loading data is expensive or slow. It's just because it's waking up. Okay. I'm going to skip over probabilistic programming. All right, good. Okay, so we load up the data. And just as a sanity check, it says, we scanned your input data, and this is what we think your variables are. Oh, and by the way, you know, this is where what Isabel was talking about. Data in the real world doesn't come nicely labeled. So you kind of have to, you know, in this version, it has to kind of guess what the types of the variables are. Okay? And this is not doing necessarily a great job. The things that she talked about will do a much better job at that. Okay? And then what happens is, this is good old-fashioned classification problem, and what it's trying to do is trying to build a good ensemble classifier. Okay? And actually, the more interesting plots are down here. Let's look at this. So there are a whole bunch of different things that it tries. Random forests, gradient-boosted machines, logistic regression, k-nearest neighbors, etc. Okay, and what's going on here? Well, there are many, many things you could try. So what should you do? Well, you try a bunch of them for a very limited amount of computation time. So this axis goes up to 2.5 seconds. You try a bunch of them for a limited amount of time. Then based on these learning curves, this is some score where higher is better. Based on these learning curves, you extrapolate, you forecast into the future with error bars the performance of the different methods. And then you say, well, which ones look promising? The ones that look promising, I'm going to allocate more resources to. And so you kind of have this racing thing where you just give more resources to things that are more promising using this kind of Bayesian optimization criterion. What does promising mean? Well, promising in this context isn't pick the single best winner. Promising in this context is find the method that is the best member of your current existing ensemble, the best addition to your current existing ensemble. So there's estimated utility per time step is the measure that we're looking at. And then this gives you sort of the stacking performance of the model that's actually built, which here in this case is actually better than any of the existing models as you get for ensemble methods. So I'm going to basically, this will continue running. But I'm going to switch to my conclusion slide. So I've talked about this probabilistic framework for machine learning and a couple of parts of the automatic statistician. And I just wanted to thank loads and loads of people that I've worked with over the years on this topic.
For one question while the next speaker sets up.
I saw Chris popping his hand up. So.
Thanks, David. I love the talk. I really love this project. My question is about the goal of full automation. I'm imagining the user of this is somebody who has lots of data. They don't know any machine learning. They want to gain insights of that data. Presumably, they have some domain knowledge. And I'm wondering if this would be even more useful if there were a way, both an easy way to inject domain knowledge without knowing all about Bayesian inference, and if there were also an easy way for that user to pose specific questions of data. Any thoughts on that?
Absolutely. I completely agree with you. I think the full automation is the moonshot, which sort of inspires you to do something useful along the way. And actually, the sort of maybe more interesting, maybe even a bigger moonshot, is to create a conversational automatic statistician, where essentially it's a two-way dialogue between the user and the system about the data. So this is a very nice domain to have a conversation because you're grounded in a data set. And there are various questions that are typical questions that you might ask of a data set, like are there outliers, or is there something funny going on this date, or something like that. So that's the sort of thing that I'm imagining. And actually, at the Alan Turing Institute, there is sort of an effort to, this project has honestly been languishing a little bit. I should have made a lot more progress over the last 3 years. But now with the Alan Turing Institute and its focus on data science, there's a good chance that we could make some more progress on that.
Okay, let's thank Subin.